Well, hello everyone. This is a video over section 6.2 on constructing antiderivatives analytically in our Calculus 1 course at the University of Montana. I'm Matt Roscoe in the math department here. So today in class we covered section 6.1 and part of 6.2. I'll go ahead and go through the slides that we got through in 6.2, and then I have 3 or 4 examples I want to work together with you, and then we'll conclude the video. So if we're constructing antiderivatives analytically, just a review of what the difference between a definite and indefinite integral is, and then the antiderivative rules. We'll talk about properties of constant multiples, sums, and differences, and then give some examples. So in 6.1, we constructed families of antiderivatives and found that the antiderivative of a function, they were always of form big F of x plus c. Here, the big F of x plus c is the result of taking the indefinite integral of f of x, which is given the notation integral of f of x dx equals big F of x plus c. So how does this differ from our work in Chapter 5 and Riemann sums? Here's the answer. An indefinite integral is an integral that does not have any limits on it. So in other words, there's no a and b associated with the integral. So what we're looking for when we use that notation is a family of functions or a class of algebraic objects, all of which have as a derivative this function little f of x dx. Whereas what we've learned before is a definite integral is an area under the curve. It's a number, so when we're given a definite integral as a mathematical task, that's what we're trying to find is a signed area under the curve, where the value of the area between the x-axis and the function, if it's above the x-axis, is positive. If it's below the x-axis, it's signed negatively. We talked a little bit and derived some of these antiderivative rules. So if I'm taking the antiderivative of a constant k, then I get kx plus c, where c is any real number. If I'm taking the antiderivative of x to the n dx, then I get x to the n plus 1 over n plus 1 plus c, where c is any integer. This is so long as x is not equal to negative 1. If I'm taking the antiderivative of 1 over x dx, I get natural log of the absolute value of x plus c. And of course, the absolute value has to come along for the ride because in the expression on the left has to incorporate both positive and negative x's, and the natural log is only defined for positive x, so we put an absolute value on it to clean that up. The integral of e to the x dx, this should be pretty straightforward. It's just e to the x plus constant. The integral of the cosine of x dx, so what function has as its derivative a cosine? Of course, that's our sine function, so sine x plus constant. The integral of the sine of x dx, well, what function would have as its derivative the sine of x? Here it's going to be the negative of cosine of x plus c. Of course, just check that in your head. If you take the derivative of the cosine, you get negative sine. 2 negatives would make a positive, and sure enough, that's what the function is over there. If we take, there is a property of constant multiples that says if c is any real number and f is a continuous function, then the integral of c times f of x dx can be written as c times the integral of f of x dx. So in words, the integral of a constant times a function is that constant times the integral of the function. We proved this statement in class. And then the if f and g are continuous functions and we have a sum or a difference, and we're taking the antiderivative or the integral of that sum or difference of two functions, then we can take the integral of f of x and add or subtract the integral of g of x. So in words, the integral of a sum or difference of two functions is the sum or difference of their integrals. And this fact we also proved in class. All right, let's get on to a few examples. So what if we were asked to find the antiderivative of this function x squared plus 4x plus 3? Let's go ahead and try that one first. X squared plus 4x plus 3. All right. So we're trying to find the integral of x squared plus 4x plus 3 dx. So, right away I see I've got 1, 2, 3 different functions being added and subtracted. So we can use our sum or difference rule right off the bat and say, well, this is the integral of x squared dx plus the integral of 4x dx plus the integral of 3 dx. So that's by our sum or difference rule. I also notice that I have two, well, I'll bring this constant out in front. I think I'll leave that constant inside. And I see I have a constant multiple here of x, so I'll use the constant multiple rule to bring it out in front. So x squared dx plus 4 times the integral of x dx plus 3 dx. I could have brought that out in front, but it would still left a 1 inside of the integral, and I think it's just as easy to leave it in and see the integral of 3 as 3x. Okay, so now I have the integral of a power, and we have a power rule that says, well, this guy is x to the third over 3 plus constant. So that was our power rule. This one is going to be 4 times, let's see, x. If we think of it as x to the first, we can use the power rule here too, and it'll be x squared over 2 plus, I'll call this constant 1, I'll call this constant 2. So that's the integral of x. And then this last one is going to be, let's see, the integral of a constant we said was kx plus c, so it'll be 3 times x plus c3. And now you have kind of this big messy thing with 3 different constants, but you know, one of the things we can do is just say, well, if you've got a constant here, a constant here, and a constant here, and it's actually 4 constants there, you add them all together, you get some other constant. So what I will do is just push all the constants to the end and call the sum of all of those constants some other constant. So we'll end up with x to the third over 3 plus, let's see, 4 divided by 2 is going to be 2x squared plus 3x plus big constant c, where big constant c is the sum of all these other constants above it. And so that's our antiderivative. Some things that you should notice. This guy we think of as f of x, little f of x, and this guy we think of as big f of x, right? And what we know is that these two are related via, you know, to get from here to here, it's integration. And to get from here to here, of course, it's differentiation. So when we get one of these, one of the ways we can check it, you know, because we got from here to here by integrating, but we can check it by differentiating and seeing if we get this, right? So here would be our check. Take d by dx of this function. I'm going to call it 1/3 x to the third plus 2x squared plus 3x plus constant. And we know how to do this quickly. I'm not going to do it slowly, but differentiate each of the parts, bring the constants out in front, and differentiate just the functions. Here I get 3 would come out in front, cancel with the 3, and the exponent would come down by 1 power. We get x squared. Here I get the 2 would come out in front, multiply by the 2, I'd get 4, and the exponent would come down by 1, so I get 4x. And here I have an exponent 1, it would come out in front, I'd go down by 1 to 0, so we get 3x to the 0, which is just 3. And here I get, well, the derivative of a constant is just 0. So indeed, what we get is, as a derivative, exactly what it should be, the function that we started with when we integrated. And so that must mean that what we got here is correct. All right, there's your first antiderivative. Let's go ahead and try a different one. Oh, you know, one of the things I was going to tell you about here while I have this sitting here is that if we go to our calculus course in the section 6 under antiderivatives, I do have a couple places where you can check things. One is this nice, I guess, site called the integral calculator, and if you've used the derivative calculator, you'll recognize it looks a lot like the derivative calculator. Let's go ahead and run the integral of x squared, let's see, plus 4x plus 3 let it go. And unfortunately, you have to look at these horrible ads, but there's one version of the integral calculator. You can let it show steps, but usually below it they'll have different versions of it, and I think this is the one that we were getting. Yes, 1/3 x to the third plus 2x squared plus 3x plus constant. And you can see there's different ways you can simplify and rewrite it. You can also show the steps if you want. You can see that they do roughly what I do. They did pull the 3 out, and then they take each piece in turn. So if we take the antiderivative of x squared, we apply the power rule, we're going to get x to the third over 3. Antiderivative of x squared over 2. Antiderivative of 1 is just x. And plugging those solved integrals into the original expression, we get exactly what we think we should. All right, so just a little bit of a nice place to check things. All right, let's go back to the slides. And here you can see that I'm asking you to do the definite integral of x squared plus 4x plus 3 from 0 to 3. And so what I'm trying to do is sort of compare and contrast a definite integral from indefinite integral. So I'm giving you here a definite integral, x squared plus 4x plus 3 dx. So think to yourself, on this one we are going to need to know what the antiderivative is, but we're going to evaluate it at 3 and 0 and subtract those results to get an area under the curve. I think it'd be worth maybe peeking at this one first. So I'll go ahead and go to the definite integral calculator on Desmos. I'm going to change the equation to x squared, let's see, plus 4x plus 3, and we're integrating it from 0 to 3, so I'll adjust the limits of integration to be 0 to 3. It's a fairly large integral because, of course, at 3 we're at a very large number, somewhere in the neighborhood of 24, yeah. And it says that the area under that curve is 36. So let's go see if we can figure that out. Verify that analytically. All right, so I need to get, no, actually I needed that back, just this one. Okay, so what we're going to do is we're going to evaluate f of 3 minus f of 0. That's the fundamental theorem of calculus that tells us how to deal with this, where f is the antiderivative of little f, right? But you see, we've already done this, right? We know what the antiderivative of little f is. So I'll just say from the last problem, we know that big F of x is just equal to 1/3 x to the third plus 2x squared plus 3x plus constant, right? Okay, so this is the antiderivative of this thing, which we're calling little f of x. So that means that the interval from 0 to 3 of x squared plus 4x plus 3 dx is going to be this function evaluated at 3. So I will put some square brackets around it, put 1/3 3 to the third plus 2 times 3 squared plus 3 times 3 plus constant minus f of 0, which is going to be 1/3 0 to the third plus 2 times 0 squared plus 3 times 0 plus constant. And you can see that all of this stuff goes away. This is all 0. I just want to make sure everybody knows that what I have here is f of 3 and what I have here is f of 0. So this whole thing is 0 plus constant. This has a minus, plus constant but a minus in between. So that means constant minus constant 0. And indeed, you'll see that happen every time. The constant will go away under integration. And so what we end up, definite integration, I should say, what we end up with is, let's see, 1/3 of 3 to the third plus 2 times 3 squared plus 3 times 3. That's it. That's the value under of the area under the curve of this function right up here. So let's see, 1/3 3 squared, 1 power 3 will cancel with 1 power 3 here, and I'll get 9. 2 times 3 squared would be 2 times 9. There's a plus in between them, I forgot. There it is. And then 3 times 3 is 9. So it looks like I get 2 9s plus 2 more, so that's 4 9s, or 36 units squared. And we already know that that's indeed true because we took a look at that already with technology. All right. Let's try this one. Find the antiderivative of f of x equal to sine of x plus 1. All right. Find big F of x, which is equal to f of x. Wait a minute. Find big of f of x not equal to f of x, where big F of x prime is equal to little f of x, right? Okay, so really what we're trying to find is we're trying to find the antiderivative of sine x plus 1, which is the same thing as taking the indefinite integral of that function and finding the antiderivative. So we can right away notice we have a sum and difference rule, so we can say this is equal to the integral of sine of x dx plus the integral of 1 dx. And let's see, the derivative of the cosine is negative the sine, so this will be negative cosine of x plus c. And this will be the derivative of x plus c. So I'll just put the c on the end, and this looks like it's going to be equal to my antiderivative. So that's our big F of x. And if we wanted to check it, what we do is we calculate f prime of x and see what happens. So if I take the derivative of the cosine, it's negative sine, so I get negative sine of x. If I take the derivative of x, I get 1. If I take the derivative of a constant, I get 0. Negative of negative sine of x is just going to be sine of x plus a 1, and indeed that's equal to my little f of x. So check, right? And of course we could check that in the derivative calculator, and I will tell you it checks. Okay, well now let's take a look at a definite integral version of this. What if I was to integrate from 0 to 2 pi of sine x plus 1? Let's do this one without peeking. From 0 to 2 pi. Zero to 2 pi sine of x plus 1 dx. I mean, one of the things you should think about a little bit is that if we had run this integral of just sine x, not sine x plus 1, then the integral would be 0 because of the way we know that sine x is shaped, right? So, I mean, just sort of thinking in your head what's going on here, we've taken the sine of x, which looks like this. If that's pi and that's 2 pi, this would be sine x. And what we've done is we've shifted it up 1, so I'll draw it a little bit lower. We know that these are positive 1 and negative 1. So shifting up 1, what that does is shift the midline, right, up 1. So we'd have something that looked like this. should go up and then down, down and then up. And so if I'm thinking about the integral, I know that it's the signed area above the x-axis underneath the curve. So I guess that's sort of the rough sketch of what I'm trying to sort of figure out here. Definitely looks like it's a positive area. I mean, if I had to guess at it, I know it's underneath this area right here, which is 2 times 2 pi, so that's, I guess, 4 pi. So it's less than 4 pi, it's less than 12. And I mean, I don't know, I'm just sort of sitting here thinking like, can you kind of call this area roughly equal to this area, kind of like a yin-yang? I think you kind of can, and that area roughly equal to that area. So my guess is that instead of being 4 pi, which is the whole thing, that we're going to get something in the neighborhood of 2 pi. Is that right? I think that is right. In fact, I can see a good argument for it that I'll come back and try to verify with. Okay, so off we go to the races. We know that the integral from 0 to 2 pi of sine of x plus 1 dx will be the antiderivative evaluated at each one of these endpoints. So it'll be equal to f of x. Sometimes the way we write it is evaluated at 0 to 2 pi, where here f of x is equal to the antiderivative of this. That's what we just did. And we found the antiderivative was equal to negative cosine of x plus x minus constant. So let's go ahead and do this. I'll evaluate it at 2 pi first. So it'll be negative the cosine of 2 pi plus 2 pi. And I guess this was a plus seed, wasn't it? Yeah. I don't know why I put in minus. So this whole thing, that's I guess what we would think of as f of 2 pi. And we subtract away f of 0, and f of 0 is going to be negative the cosine of 0 plus 0 plus c. And this thing we call f of 0, right? Okay, so now we just need to fill in some numbers here. I need to kind of think about the cosine and what this thing looks like. So the cosine looks like this. That's 2 pi. This is pi. Okay, and we're supposed to take the opposite of the cosine of 2 pi. The cosine of 2 pi is 1. So we'd have the opposite of 1 plus 2 pi plus constant minus the opposite of the cosine of 0. Cosine of 0 is 1. So I would take the opposite of 1. Opposite of 1 plus constant. So let's just see how this works out. For the first one, I get negative 1 plus 2 pi plus constant. For the second one, I get plus 1 minus constant. Constants will go away. You can kind of just, well, you can always ignore them under definite integration because they'll show up here and here. One is positive, one is negative. And the 1 and the 1 go away, and we get just 2 pi as our answer. And I'll tell you what the realization I made when I was sort of looking at this. I was thinking like, okay, couldn't you just sort of chop this thing right here and take this whole thing and sort of replace it up here, right? In other words, that red area and that red area are the same. If I replaced it and put it up there, then I would have something that's 2 units high, pi units long. So in other words, the area under this curve is 2 pi, and that's indeed what we got. But let's go ahead and check it out anyway. I'll do sine x plus 1. There it is. We're going to integrate from 0 to 2 pi. Okay, so there's your picture. It's not a very nice picture as it stands, but I guess I can clean it up. I always like with these trig ones to go, in multiples of pi, so negative pi to 2 pi on the x-axis and step by pi. There we go. So we can see here's where pi is now, and this is the piece right here and here that I said fit over the top right there and there. So it does look like, and indeed you can see that the value of the integral appears to be equal to 2 pi, just like we thought. Okay, one more and we'll call it a day. What if I was asking you to find the integral of the antiderivative, of f of y is equal to 1 plus y squared over y. And then I'll just preview the next one, integrate it from 1 to 4. Let's see, so let me make this as large as possible. Okay, so find f of y such that f prime of y is equal to 1 plus y squared over y. All right, so off to the races we go. We want to know what the integral of 1 plus y squared over y dy is. So we want to find the antiderivative here. At first glance, you're like, well, I have no idea, right? Because I've got I don't know any function sort of off the top of my head that looks like this. But this is one of these where if we rewrote it a little bit, it might be a little bit easier. We could rewrite it as 1 over y plus y squared over y dy, which we then could write as the integral of 1 over y dy plus y squared over y. Well, that's just y dy. So splitting it up using the sum rule. And then 1 over y, of course, is the natural log of the absolute value of y plus constant. And the integral of y is going to be, let's see, y squared over 2, right? And since both of them have a plus c, we put a plus c on the end. And checking it, of course, you'll find exactly what you think. The derivative of this is that. The derivative of this is that. Put those two together, we get this. Multiply top and bottom by y, we are putting it over common denominator, then we can go ahead and write it as 1 plus y squared. So we did find the antiderivative. Now let's go ahead and move on and do the definite integral problem. So we're trying to find the derivative from 1 to 4 of 1 plus y squared all over y dy, which is going to be equal to f of y evaluated at 1 to 4, where f of y we found from the previous step. That's just the natural log absolute value of y plus, I'll call it 1/2 y squared plus constant. Okay, well, that seems fairly straightforward. Let's put a 4 in there. We get natural log absolute value of 4 plus 1/2 4 squared plus constant, that whole thing, minus the natural log absolute value of 1 plus 1/2 times 1 squared plus constant. Again, this is f of 4, and this one is f of 1. A few things come to mind here. The constants are going to cancel because one's positive, one's negative. If I take the natural log of 1, that's going to be a 0. And I think everything else can go ahead and simplify. The absolute value of 4 is just 4, so I can write this as the natural log of 4. 1/2 of 16 is going to be 8, minus 1/2 of 1, which is 1/2. So what do we get? We get, let's see, if I put this over 2, it'd be 16 halves minus 1/2 would be 15 halves. So the natural log of 4 plus 15 halves, if you like, as is our answer. Let's go ahead and see if Desmos checks it out. So we're trying to find the integral of the function 1 plus y squared. Oops. Probably have to put parentheses around it just to make the whole thing be on numerator. 1 plus y squared divided by y. And we're integrating from 1 to 4. Okay. And, oh, I see f of x and I have y here. Yeah, so let's just make the function in terms of x instead of y. There it is now. I see the function. Let's get some labels on this. We don't need to be in multiples of pi anymore. So let's go from -1 to 5 by 1s just to make sure we can see what we're doing. So just looking at the graph, I can see that each one of the rectangles is a unit. And so 1, 2, 3, 4, 5, 6, 7, 8 or 9-ish is sort of where I'm at. And indeed, that's what we're getting for a number. To see if we have the right answer, I guess we can plug in the natural log of 4 and add to that 15 halves. And indeed, we get the exact same number, right, as we do here, the one that the calculator is getting using Riemann sums. And so pretty neat. You can definitely find the area of even complicated shapes like this function, the area under its curve. All right, I think that's about it for today. I think that's my last slide. Yep, it is. So you've seen 4 different examples of computing both indefinite and definite integrals, and you've been given 3 or 4 new rules for integration today. I would encourage you to try some homework and see if your understanding is developed enough to complete the homework. That's about all I have for today, and we'll see you when I get back on Wednesday. Thanks for watching.